All right, this section is on solving systems of linear equations by graphing. And as a little warm-up, we'll look at the graphs that are on your notes. And just to remind you, you're going to need graph paper for this section of notes because the graphs on your handout that I gave you are way too small. So anyway, when we look at these, I would say let's look at the y equals x squared first, because if you think about, okay, if you put in 0 for x, 0 squared is 0, so we know that's at 0, 0, the only one of these graphs that goes through 0, 0. And then, so we know it probably has to be this u one. But then if you take, and that's called a parabola, actually. But if you take 1 and square it, 1 squared is 1, right there. And if you take negative 1 and square it, negative 1 times negative 1 is also 1. If you take 2 and square it, you get 4, which is right there. You get negative 2 and square it, you get negative 4. So when you connect those dots, you get it's called a parabola. So that goes with 4. And then if we look at these other three equations, they're all in slope-intercept form. So if you look at the slopes here, that's going to be a 1, and a 2. And then if you look at these numbers back here, these are the y-intercepts. And that's, remember, the form y equals m, slope, times x plus b, and b is the y-intercept. So if I look at this equation, number 1, and I say the y-intercept is 2, well, this line right here, going through 2 on the y, that would have to be that equation. Well, let's just check and make sure it's got a slope of 1 over 1. So if we start here at the y-intercept 2 and go up 1, right 1, yes, we run into this line. So that's this line here goes with 1. Then 2, it's negative 3 y-intercept, so that's got to be this line. And if we check its slope, it's got to be 1 also, so we'll go up 1 and right 1. Yep, that's right. So the last line right here would have to be this number 3, and it has a y-intercept of positive 3, so that would be that. It's got a slope of 2, or 2 over 1, so if we're here and we go up 2 and right 1, we'd be at 1. And if we went down 2 and left 1, we'd be at this place where these two lines and this parabola all intersect at this point right here, which is negative 1, 1. Now, what we're looking at today has to do with the fact that if we have two equations and where they intersect, that can be a solution. So that's where we're headed right now. All right, so our first problem is a bus leaves the school traveling west at 50 miles per hour. After it travels 15 miles, a car follows the bus traveling at 55 miles per hour. After how many hours will the car catch up to the bus? So I don't really like this the way this is worded, but I think what they're saying is that the car leaves the school after the bus has gone 15 miles, and it's going the exact same path as the bus. So it's following it 15 miles behind, but it's going faster, so it'll finally catch up. So what we want to do is look, there's two equations here, and it says how many hours. We're trying to find out how many hours it's going to take for the car to catch up to the bus. But there's another unknown here, because not only do we need to know how many hours, but we also need to know how many miles they're traveling, because we have miles per hour here and miles per hour here. So we have two unknowns. Okay, so if we let t equal the time in hours, that's what we're trying to find here. And if we let d be the distance in miles, then we can set up our two equations. So for the bus, first of all, the bus, okay, they go 15 miles ahead of the car. So at their speed, which is 50, if we multiply that times the time, for example, if it was 2 hours and they went 50 miles per hour, they would actually travel 100 miles. But they've also traveled this 15 here. So their equation is going to be distance equals 50 miles per hour times the time that they traveled plus 15. We're trying to find out the time where they meet. Well, then the car's distance would be 55 miles times their time, but they're taking off 15 miles behind them, so they would be at D equals 55 times time, because they're 15 miles behind. So if we graph these two equations and we look at where they intersect will give us the coordinates of these 2 points, and we'll be able to tell the solution. We'll be able to tell the time, because the distance is the same for both cars. They both are the bus and the car. They're traveling the same distance. Now if you'll pause the video and then do your graphs on the graph paper and set it up and draw it like it is on the your notes, and then if you'll come back, we'll look at the graphs and see if you graphed them correctly. All right, so if we look at the next slide, if we graph each equation, okay, I'm going to go back for just a second. Okay, so the blue one is D equals 50t plus 15. So the blue line here, if we're at 50t times or plus 15, that means it's going to intersect the y-axis at 15. And right here's 25, so a little bit below that, they've got 15. And then it's going 50 miles, make sure, whoops. Okay, it's going, the slope is 50 over 1. So if we're at 15, and 15 plus 50 would be 65. So if we go up 60, or if we go up 50 and right 1, so we'd be at 65. So there's 50 and there's 75, so 65, and then over 1, we'd be at 1 hour. Okay, and then if we went up 50 more, we'd be at 2 hours, and so on. So if we went up to 65 and then we went up 50 more, we'd be at about 110, and that would be at 2 hours. Okay, so then the red one, the red line, the slope is 55 and the y-intercept is 0. So this is one that is proportional because it intercepts the y-axis at 0, 0, and it goes up 55. So if we're at 0 and we go up to 50, a little bit ahead, and then over 1, and then if we went 55 more, we'd be at 110, and we'd be at 2. And then here's where the 2 should intersect. So they should intersect at the 3rd hour. They both go 165 miles exactly. So by your graph, it should be 3, 165. So then we can plug in and see if that works. So our first equation, we'd plug in 3 for t and 165 for d, and 3 times 50 is 150, plus 15 is 165. Then if we plug in 3 for the next equation, whoops, then 3 times 55 is 165, so that works. Alrighty, so let's go on to the next equation. Okay, so in 3 hours, whoops, I guess in 3 hours they would catch up, and it would be at the 165-mile point away from school. Okay, so not all systems of linear equations have graphs that intersect in one point. There are 3 possibilities for graphs of systems of 2 linear equations, and each represents a different solution set. So first of all, we could have intersecting lines like we just had, and there's going to be one solution. So you want to fill that in on your notes. Then we could have parallel lines where they have the same slope but different y-intercepts. That means there'd be no solution because they never intersect each other. And then for the last one, same slope, same y-intercept means it's going to be the same line right on top of the other one, so infinitely many solutions. All right, so our next one, okay, we've got this one in slope-intercept form, and we're just going to solve for x and y. This one we don't have in slope-intercept form, so we need to get it to be y equals something times x plus 3. So this one's already ready to go. Y equals 2x minus 7. And then 3x plus y equals 3. We're going to subtract 3x from both sides to get y alone. So y is equal to, now I would put the negative 3x first and then the plus 3 because it looks like the same form as this where you can see the slope. But here's the slope right here, and it's going to be negative because plus a negative, you change subtraction to adding the opposite. So if you'll graph those two equations, and we'll see where they intersect. So pause your video and go ahead and check that. All right, so once you graph it, and we look at the red one first, so that means we're at a y-intercept of -7, and then we're going to rise 2 and run 1, rise 2 more and run 1, rise 2 more and run 1, and so on up. We can draw the line. So the other one is going to be y-intercept of 3, and so that one, negative slopes, we're going to go from 3, we're going to go down 3 and right 1, down 3 again and right 1, and that's the intersecting point. So they intersect at 2, -3, and we can plug those back in and check. So if we plug in 2 for x and -3 for y, that's going to be 4 minus 7, which is -3. The other one, we're going to put in 2 for x and -3 for y, so 6 minus 3 or plus -3 is 3, so that one checks. All right, so our next one, we're going to get them both in slope-intercept form. So when we subtract 2x from both sides, we get y is equal to -2x plus 9. And for the other one, y, well, let's see, we'll add 9 to both sides. So y will equal 2x plus 9. Now notice it's the same equation. So when you go to graph these, and then we right on top of each other. So the red one, we're at 9 on the y-axis, which is a little off the graph, but on your graph paper you can do it, and then go down 2, right 1, down 2, right 1, plenty of points, so we can draw that line. Well, the other line's the exact same thing, so we put the blue on top of the red, it turns purple. So any point will fit in there. It doesn't matter what two coordinates. So if I pick this coordinate right here, we can go 2, 5, and 2, 5 would fit. We could go 4, 1, and 4, 1. X is 4, y is 1 would fit. We can do one of these fractional ones, but it's hard to see them. But anything on this line will fit into those two equations. And that's just a formal way to show it. Okay, so the y's need to be equal and the x's are also equal. When we solve it, the x's drop out. So all real numbers work because we got a true statement. All right, next one. Okay, this one's already in slope-intercept form, so we'll get the 5x plus y. We're going to subtract 5x from both sides, so we get -5x minus 1. So now you're going to graph both of these, and then turn the video back on, and let's look at the graphs. All right, so when we look at the graph, we're going to go to +1 on the y-intercept, and then we're going to go down 4 and right 1 and draw that line. And then for the other one, we're going to go to -1 on the y, and we're going to go, let's see, we're at -1, and we're going to go, we could go up 5 and left 1, up 5 and left 1, or we could go down 5 and right 1. And those two lines will intersect up here, kind of hard to see, but they will intersect at -2 on the x and 9 on the y right here, I'm sorry. And so if we plug those in and check them, they work as well. All right.